Okay, start.
Very good evening to all. I, CRCY, extended a very warm welcome to all of you to the fifth day of National Enrichment Program in Mathematics 2021 conducted by the Department of Mathematics, Sacred Heart College, Chalakudi. The aim of this program is to enhance the mathematical skills and knowledge of aspiring students. Honorable Chief Guest, Dr. Meenu Mariya, teachers, my dear participants, I would like to welcome you all for taking the time off of your heavy schedule and making these hours with glorious presence. Let's begin the formal session by evoking the blessing of the Lord Almighty. For the same, I invite Ms. Amrita VC of 2nd PG Mathematics, Sacred Heart College, Chalakudi.
ഈശ്വര ചൈതന്യം ജീവാമൃതം ഈ പ്രപഞ്ചത്തിലെ സ്നേഹാമൃതം നിറയട്ടെ നിറഞ്ഞൊഴുകിയിടട്ടെ മാനവഹൃദയ നിലങ്ങളിലെങ്ങും ഈശ്വര ചൈതന്യം ജീവാമൃതം ഈ പ്രപഞ്ചത്തിലെ സ്നേഹാമൃതം.
Thank you, Amrita. Now, I would like to call upon Ms. Smita Davis, the Assistant Professor, Sacred Heart College, Chalakudi, for introducing our chief guest.
Hello, I'm audible, right?
Yes, yes.
It's my extreme pleasure to introduce the resource person for the day, Dr. Meenu Mariya. Uh, she is junior to me and Lynette at Cochin University of Science and Technology, a person who I can definitely call as my little sister. She should be a real inspiration to the all math aspirants present here today. At such young age, she has completed her PhD and alongside she is carrying all her passions along with. It's really a hats off to Dr. Meenu Mariya, and it's she has done her PhD. She has done her graduation in mathematics from St. Stephen's, Delhi, and post graduation from Cochin University of Science and Technology, as I mentioned. She has done her PhD from Victoria University of Wellington, New Zealand. Her thesis is entitled On Metroids that are transversal and co-transversal. She is currently statistical and data analyst at Stat New Zealand. And as I said, it is it will be a real word session because she's a person who is very presentable and very good in dealing people. Thank you, Meenu, for in your busy schedule, you have accepted our invitation and shown a great grace to be present with the young aspirants in mathematics. So, students, explore maximum, respond to her maximum. Okay, thank you.
Thank you, Smita Miss. With great honor and respect, may I invite our chief guest, Dr. Meenu Mariya, the Statistical and Data Analyst, Statistics New Zealand, for taking today's session. It's my pleasure to welcome you, ma'am, for this National Enrichment Program. Ma'am, please.
Um, Hello, everyone. I must say the pleasure is definitely mine. I especially thank Smita Chechi, that's what I call her. But it's your Smita ma'am. And also Lynette, we were at COSAT and I was their junior, so it's definitely my pleasure and privilege to be invited to speak to their students. Yeah, so I would like to see this as an interactive session between us. I'm trying to maybe tell you about matroids in not great detail, but at least from the perspective of graph theory. And if I will explain what graphs, starting with graphs, and we will go through some of the properties. But please feel free to ask any question you have during the session. You can raise your hands or even message in the chat. I will keep an eye on that. And we'll sort of collaborate and understand what's going on here. It's a tiny bit of knowledge sharing. That's all I intend here. And if you learn anything about matroids from here, that is a win-win situation for us both. Cool. So I will start sharing for us to see. So just a moment. Okay. That should be visible now.
Yes.
Okay, cool. So as I said, I'm not sure if any of you have heard of matroids before. Is there anyone here who knows what matroids are or have come across them at some point? Maybe a show of hands if you have. Okay, I wasn't expecting many hands to go up anyway. I discovered them at the end of postgrad when we were asked to do a project at CUSAT. And before that, I had no idea what they were. But my journey with math started when I did not get entrance into an IIT. And I was like, okay, if it's not an IIT, then I don't want to do engineering and I'll try what else I like. And I was like, oh, I like maths. Maybe I'll give it a try. And decided to pursue that. And it was in second year when we were introduced to real algebra that I really, really started enjoying mathematics. And then in third year, I was introduced to graph theory. And then I was like, yes, I totally love this. Like, why weren't we introduced to any of this in school? Like, it's such a shame that school students don't see any of this. And in postgrad, when I came across this term, it sounded very computer science like to me. So I was like, oh, this is probably not pure mathematics. It might not be, my cup of tea. And then I realized, oh, wow, this is a perfect amalgamation of ideas from linear algebra and ideas from graph theory. And you sort of put them together in a mix and understand there is another structure that is both a graph sometimes and a vector space sometimes. And that's what matroids are. And that was the introduction that I got from a paper that I read, which I will link at the end. So it was in 1935, which is a quite young age for a new subject to form, given the age of mathematics. And there we have results going back to BC. 1935 is a very, very young age for this subject. So it's definitely still in this baby phase. So it was in 1935 that Hassler-Whitney writes this paper, which is on the abstract properties of linear dependence. Can also be said as the properties of linear independence. So he came across some properties of independence or dependence, which were seen in vector spaces, and he saw the same thing happening in graphs in graph theory. So if you Google matroid theory, you'll see quite a good introduction in terms of vector spaces and graphs. So what I'd like you to guide you through today would be through the language of graph theory. So everyone here has seen a graph is what I've got now, but just to refresh your memory, we'll quickly go through what that is. So a graph, you can define that on instead of dots and lines. So you have your dots called vertices and your lines called edges, and you can have any sort of like relationship between the dots and its edges that connect the dots. So if you have a simple graph, then you only have one edge connecting two dots, but you can also have non-simple graphs that have multiple edges between vertices. So you can have loops, which is a vertex connected to itself. So it's basically dots and lines, and you can easily explain this to a 10-year-old, and we have explained that to 10-year-olds, we being me and a couple of my friends here. We go around and talk to students in schools when we have the time. Yeah, so this is a graph, and a tree is a graph with no cycle. So I guess we have to start what cycle is. So if you start at a vertex and walk along the graph, and then come back to the starting point without repeating any edges, then you get a cycle. So you start and end at the same vertex, and you can have any number of edges in between. You just have to not repeat any edges. So here you get a cycle, and a tree would be any set of edges in the graph that do not contain a cycle. So for example, if you look at this set of red edge here, there are 3 red edges that I've chosen, and they start at one vertex, end at another, and they do not contain a cycle. So this gives us a tree in the graph. Now, a forest in the graph is a collection of trees. So I do have to mention connectedness before that. So a connected, you have connected graphs when every vertex has, loosely speaking, everything is connected to each other, so you don't have bits and bobs sort of floating around without edges in between. So if you had, say, if this was your whole graph, then that would mean this was your whole graph. That means you have 2 disconnected components. So you have one component up here, C1, and the second component down here. So it's not connected. Whereas for a connected graph, so say your graph only consisted of this component, then it's a connected graph because everything is sort of joined with each other. There are no loose components floating around. So I'm trying not to go into the very formal definition of things. Now, you can have, say, I'll just make this graph a bit more bigger to explain what forests are. Say your graph was a bit more bigger, and you wanted, so you've got your red tree, and then maybe you wanted to join this edge to this green edge. So the green edge, along with the red edges, they form a forest because it is a collection of trees. Okay. I think that's all the basic knowledge we need to know about graphs to proceed. Do I have any questions to answer at this point? Is there anything that is unclear? Okay, if that's the case, we can move on to the next slide. So what are the forests in this graph? Just out of curiosity. So that would be our sort of starting point. We're going to explore what the forests are in this graph. So say I'm going to write that. I'm going to call it a sort of a weird name, which will become apparent later. So I'm going to call it a curly I. If you had like proper printing, this would look much better, but forgive my weird looking curly I. So say I'm going to call a set of all forests curly I. Now, what would be contained in that set if I had to pick forests in this graph? Any suggestions? So here I have named the edges of the graph, and I'll explain later why, not the vertices of the graph. So it's the edges that we care about. So what collection of edges give me the forest in this graph? It's quite a few, so I think there should be enough for everyone to have a go, sort of. Any suggestions? You might be right. You don't have to be wrong. Like, there are no stupid questions either, so we can give it a try if anyone has a suggestion. You can just tell me the letters from the graph, the edges that correspond to the forest. No? Maybe I'll start off, maybe give an example. So we could maybe just go by the number of edges. So if I start with a 4-edge forest, is it possible to have a 4-edge forest in this graph? So I should be able to pick up 4 edges such that I don't get a cycle. Is that possible in this graph? So let's say I choose 1, 2, so I choose C and B. 3, so I can't really choose A because that's a cycle in itself. So once I choose these 3, I've got 2 options. I can either go to F or I can go through D. Now, if I go through F, then that means I've formed a 3 cycle in there with B, F, and E. So I can't do that. The other option for me is to go through D, but that also forms a cycle. So I can't go that way either. So there is, and you can do this for other set of starting vertices too. So wherever you start, you can't pick 4 edges from this graph so that it's still a forest or a tree. Or the idea is it shouldn't contain a cycle. So we can't do that with 4 edges. What about 3 edges? So I sort of have given away the answer there. So you've got C, B, and E, which are 3 edges in the graph, and they do form a forest. So you have C, B, and E forming one forest in the graph. What are other kinds that I can find? Something that's, is there any other 3-edge forest? Oh, sorry. Yeah, I've just noticed the chat. Hmm. Sorry, I'm trying to access. Yep, there we go. So it's not possible. Yes. Oh, this is very interactive. I quite like that. Sorry, I missed that earlier message. Okay, so yes, it's not possible with the 4 edges. It's pretty good. And you also have C, F, E. Yep. C, D, E. So if I were to forego the labeling, then all of these are basically the CBE, CFE looks like that, CDE looks like that. So I have, how many of those do I have? Trees or forests that look like that, sort of an E without the middle, slash, dash. How many of those can I expect? There's CBE and sort of go around it. 3, 4, 5. So there's already 2 mentioned. Yeah, it's 4. It's pretty good. So yeah. So we can expect 4 of that kind, and then we have the zigzag one. So sort of like a Z. How many of that can we expect? I think I'll maybe start sort of labeling them like that. It makes a bit more interesting that way visually. So I is still the same set. I'm going to still call it curly eye, but I'm just going to draw the different kinds. How many of the curly ones do we have? 4 curly ones. Yes, so we can go sort of the Z sort of facing up and down, and then we also have the sidewise ones. So we can go like B, F, D. So yes, the labeling does matter in this case. Yes, they need to be labeled. So there's 4 of that kind. So that is to do with the 3-edged forests now. So that's 3 edges. Now what about 2-edged forests? How many of that can we expect? There's how many? Oh, actually, we're missing one more kind. What's one more kind there we can see? So we've got the E without the dash. We've got the Z. There's one more. That's a 3-edge. So give you a clue with that. So we need to pick 3 edges. And so far we've managed to sort of go, keep walking or do their like crazy walk. But what if we can't sort of keep walking, but instead have to send, if you start at a point but you go in different directions, you can't really do the walk like thing. So it will look something like that. This edge here, B, and F and C. So that is also a three-edged forest, three-edged tree in the graph. So you also have the graphs that look like that. And this gives you, so you can get two kinds of that with the labels. Cool. Now with two edges, what can we get with two edges? So it doesn't have to be connected because it's a forest, remember? So you can get a bit of a variety there. What are the two-edged ones we can get? Maybe I'll start off with a hint. So with two edges, we can maybe go, to go the path of the disconnected ones, I can try C and E. So that would sort of look like that if I were to draw it. So I have trees that look like that. I'm sorry, forests that look like that. And what else can I have in in the two-edged one? Is there a connected? Acute angle and right angle. Nice. Like that bit of geometry in there. Yep, so we can have edges that look like that. Sort of BF, for example, or CF. And you also have the ones that look like that. So BE. So I did start off with a, enumeration, but more than that, it's the different kinds that I sort of wanted to bring to your attention. So you have three-edged ones, you have two-edged ones, and they're all forests. And you also have single-edged ones where you basically just pick each edge. That is also a forest in the graph. Is that all? Do I have all different numbers of graphs? Or am I missing something? So I can pick three-edged forests, I can pick two-edged forests, and I can pick single-edged forests. And we know that we can't pick four edges. So because we can't pick four, that is also, anything higher than that is also out of the box. Are we missing anything else, or have we exhausted all the different combinations of forests that we can find from the graph? So I'll give a tiny hint there. We can also think of the zero-edged graph with no edges, or in other words, it's the set phi. That is also a forest in this graph, right? Yes. But yeah, so if vertices, which is in the language of edges, would be no edges, right? Zero edges. Good. So some of the properties now, if you were just looking at these different forests, there's something in here. So one interesting fact is this, that phi is an element of I. So I is, the curly I is what we called this set of forests. So phi is an element of I. Another property that we can notice is, say I pick what have I already drawn that? Maybe I change this drawing to look like that. So say I pick this forest, and now I already know it's a forest, but if these were the same set of edges, if the labels corresponded, then we know that this set, say I call it I1 and I2, I2 is a subset of I1. Okay? I2 is one edge lesser than I1, and we know that I1 and I2 are both in I, in curly I. And if I were to remove one more edge from I2, say I were going to remove that, I still get an independent, I still get a set of edges that is in I. And if I remove that one too, then I get phi, which is already in I. So this is another property that we can observe in the set of all forests, is that if you take a forest and you look at a subset of it, that will also be a forest in the graph. Right? So it's quite easy to see in this example, and you can observe in general. Like I said, we're going to stay away from formal definitions. For that, you can definitely refer to the textbook, which also I will put in the link at the end. So that is another interesting property that we have in the set of I's. So what I'll do is I'll go ahead and write those sets. So I've written axioms for independence, but don't worry about the big words. We'll just write down what we've observed so far. So I'm going to call that first sort of observation as I1. And that observation is that phi, the empty set, is an element of curly I. And the second observation is that if we have two sets, say I1 and I2 in curly I, and we know that I2, my bad, we just know I1 and I2, sorry, we don't know about I2, we only know about I. We did pick something before that was in both, which is what confused me a bit. So we know that I1 is a set in curly I. Oh, technology, what's happening? Okay, so I1 is in curly I, and we know that I2 is subset of I1. If we know this is also true, then we can say that, maybe I'll name these. We can say that I2 will also be in curly I. So if you take any set in curly I, look at all the subsets, they will all be in, they will also all be members of curly I. Okay, and we go all the way down to the empty set. Now there is a third property in here that is not that evident, but we'll take a couple examples and sort of tease out. So this is a graph from before. I've redrawn it here. So we're looking at the two sets, I1 and I2. So I1 is the set B, C, D. It sort of goes around the graph. And the second set, which is I2, is BE. So it's that sort of right angle at the corner with the loop at one vertex. And they're both in curly I, so we already know that they're both in curly I. They're both forests. Now, I want to find out an element X, element being, sorry, I should use the right word, edge. I want to say, I want to use an edge X such that I can take X and add it to I2 and still be, sorry, that's not what I want. I still want this to be element of curly I. Okay, is it possible for me to find something that is another edge? Now that's not already in I2, but I can add it to I2 and still be in curly I. That is, still be a forest. So I'll just highlight those for better ease. So this is I2. This is I1. So I2 consists only of B and E. Is there any other edge in the graph that I can add to I2 such that after the addition, it is still a forest. So for example, if I add F, I have a problem, right? Because BEF is a cycle and it's no longer a forest in the graph. But what about D, maybe? Oh, cool. Touch wood. We say that at the same time. No, kidding, that's superstitions. Anyway, so we have D. That is not in I2 already, but if I add D to I2, so we have I2 union E. This should be an X, my bad. I2 union D, which is B, E, D, is still a forest. Now, in fact, if you look at D, that is chosen, that is already a member of I1. So this is a small graph. So we will sort of end up, the edges will sort of overlap each other. But even if this weren't the same graph, even if we have really, really, really big graphs, we can always find something in, if I1 and I2 have anything in common, and even if they don't have anything in common, you can always find an element that is in I1, but not in I2. That's all that we need. So we can always find X element of I1, but not I2, such that I2 union X will still be in curly I. So this is the this is sort of a special property, which is not that obvious. So this is something that you can also see in the world of vector spaces. If you look at vectors that span a vector space, you can do the same sort of thing, and it will become a bit more apparent when we look at another set involved. But for now, this is the third property that we're involved that we care about. So I'm just gonna add a set here. So we have our two properties already, which were I1 and I2, that we already have the empty set in curly I, and then we know any subset of an element of curly I will also be in curly I. And now the third property that we're interested in is, call it I3. So if we have I1 and I2 already both in curly I, such that I2 is smaller in cardinality compared to I1. That's all we care about. It doesn't have to be a set or subset. It don't have to have intersection elements. It just has to be one set has to be the smaller size. No, that is a strict inequality. If they're the same sizes, this doesn't have to happen. Then there exists an element in I2. The other way around. An element that is in the bigger set, which is I1, and not the smaller set, such that we can add that extra element that we found, E, to I2, and that still will remain a member of the curly set, curly I. Okay, so this is a third property that we're interested in, and together, all of these three axioms together form the axioms of independence in matroids. So the idea is, if you can find a set of something, in this case, in our graph picture, we have E, which is the set of edges in the graph. And this E can be anything for us. Like I said, in the context of graph theory, this will be the set of edges. And if you can find a set curly I that obeys these three axioms, I1, I2, I3, then that structure is a matroid defined on E. So just want to be a bit careful here. The graph is just a graph. We have vertices, edges, they have relations. But when it comes to the matroid, the graph is giving rise to a matroidal structure on its edges. Okay, so it's the edges that we care about and how they interact with each other, forming a forest, not forming a forest, and so on. And that's what we care about. And if they obey I1, I2, I3, any structure that obeys I1, I2, I3 is a matroid. I didn't think I would actually define matroid in a long, long time. We usually try to stay away from them, even during conferences. So this is a new thing that I've done. The other thing is, like I said, I'll have a couple of links to papers that explain what happens on the vector side of things. So if you look in vector spaces, you can find vectors that obey I1, I2, I3, which then gives rise to matroids in vector spaces. So the same kind of properties apply in two very unrelated areas. Well, not totally unrelated, but not seemingly related areas. One's vector spaces, that's linear algebra, and on the other side you have graph theory, and it's not a trivial thing to observe. So Whitney and also 3 other Howard students, I don't think I'll correctly say all of the names, so I'll say the 3 Howard students, which you can find in the article at the end of the talk. They were quite clever to discover this sort of seemingly different set of things to share the same properties, and that's one of the beautiful thing about mathematics. You go around seeing all these different relations that other people don't see, seeing patterns that other people don't see. Cool. So now we've defined the forest, we've looked at all of them, but what are the maximal forests in this graph? So maximal means you can add an edge and that will delete the property of being a graph. So sort of not the maximum, so it is, you will see later that that will also be the maximum, but maximal just means you've got a forest and you add something else to it, it is no longer a forest. So what are those kinds of forests in this graph? So if we go back to our different kinds of forests, these are all the kinds of forests that we had. And now we know that they're in curly I and they form this special set of edges. And sorry, I forgot to mention something. So this is called the independent set. That's why the I. So this is the independent set of elements in the matroid. Now, in our case, the independent sets are precisely the forests, or the set of all forests in the graph. So now that we know independence, what are the maximal independent sets in the graph? So we know by property I2 that any subset is an independent set. And we know that if we have a sort of smaller independent set by property I3, we know we can keep augmenting it. We can keep making it bigger using another bigger set, such that that bigger, the new bigger set is also independent. So we can keep growing that smaller independent set. So in that case, what is something here, or is there a kind of forest here such that you add an extra edge and you destroy the fact that it's a forest? So you destroy its independence by that. Is there any kind like that? CFB, yeah, so that's pretty good. So CFB is that sort of, star-like thing you have here, or it's this last kind. And any edge you add there, you get a, you're no longer a forest, right? And the same thing also happens with this kind, the Z kind of forests. It also happens with this kind. So you see that all of those maximum forests here are also the maximal forests, right? The forests with the highest number of edges also give you the maximal forest, the maximum forest in this graph. So one thing we notice is that they're all the same size. They're also the maximum size. Now, we know that, so let's write one of the examples. So CFB and all other 3-edged forests. So we notice that they're of the same size. Now, we're trying to derive a new set of axioms using the axioms that we already have for independence. So we know that the empty set is in curly I. So empty set is independent. But we also know, so we know the independent set is there. If we don't have anything, if we don't have any other set that is maximal, we at least have the independent set, right? So we can always guarantee the set of maximal forests will be non-empty. So I'm going to call this set curly B, and it's going to be my first axiom here. Curly B, almost sounds like Cardi B, will never be empty. Okay, that's my first observation, because I know if everything else fails, I know that the empty set will be in curly B. Okay, what else can I observe using? So we've used I1, and we can't really use I2 because we're not looking at subsets here, right? So we know that because they're all the same size, we can't have the subset relation going on. But can we maybe sort of, change I3, the third axiom, to mean something different when they're all the same size? So we know here we're actually augmenting, we're taking the smaller independent set and trying to grow it. Is there a way for us to maybe not grow the things, because we already got the biggest forest that we're looking at, and we know that this condition has to hold, that they have to be strictly less than each other. So, but here we're looking at elements that are the same kind, the same size. So we can't really do that. But there is something else that we can do. So we know that there, if we take two elements of curly B, we know that they're going to be the same size. So if I'm going to add something, because it's the maximal, clearly it's going to not be in curly B. But when I'm adding something, I can also try and take away. Right, so I have a forest, say I have this. And if I add an edge here, what happens? I get a cycle. But by adding one, after adding one, I can also take away one, such that I get a new element now. And that's still in curly B because that's one of the maximal ones. Right, so this is sort of loosely trying to explain second axiom here, which is B2. So if we have B1 and B2, both elements of curly B, and X is element of B1 minus B2, so here we do need them to have an intersection, then there exists a Y which is in B2 minus B1, such that we can add the Y element, but we take away the X element. And this will still be an element of B. So we can always find that one element to take away from one of the maximal forests, and we'll be able to add another one, where one is in the first one and not in the second one. So we choose those elements accordingly. We'll always be able to choose these elements such that we can sort of replace an element in the maximal forest. And these maximal forests are called the bases in the matroid. So all of these maximal forests that you're seeing, they're bases in the matroid. And these are actually called the basis axioms. So what we've really done here is something quite, what's the word? Clever is not what I'm trying to say. So it's a pattern inside matroid. So what's happening is we have the set of axioms of curly I of independent sets, right? So we have I1, we have I2, we have I3, and they all, if there's any structure that obeys that on a set of elements, we get a matroid. In the same way, exactly the same way, there's an equivalent definition by using maximal forests, or maximal elements, maximal independent elements. If we choose B1, so it's and B2, the two axioms, then we can still define matroids where the elements that are in curly B, they form the basis of matroid. So we already know that in the graphs, we have our maximal spanning forests, and in connected graphs, they're just the spanning trees. So spanning trees in a graph are the maximal trees that you can find in the connected graph, right? Where every vertex is has an edge in that tree. It's connected to an edge in that tree. So it's the spanning trees that form the bases in a graph. Whew. Oh wow, okay, I think we're going good for time. I might not be able to get through everything, but that's still fine as long as I have your participation, which has been pretty good. So any questions that I have? Cool. So we can move on to the next one. Just an illustration of B3. So I think I just showed you that in the previous. In the second axiom, B1 can be empty. Yes, but if B1 is empty, so this is another observation that we have. That's a good question, actually. The observation that we have is if B1 is empty, then automatically B2 also has to be empty, right? Because they're all of the same cardinality, because they're all the maximal ones, and because we have I3 such that you can keep, I2 that they keep augmenting. So if B1 is empty, B2 is also empty, so it all becomes vacuously true. Then it's going to be a bit trivial, but yes, it can be empty and it will still hold. Good question. So this is just B3 in action. Like I quickly showed before, if you have B, C, and F in there, and C, D, and E, you can choose, you have to choose one element to take away if we want to create B3 from B1. So say I'm going to take away, if I say that is my X, sorry, that's the one that I'm going to add. And the one that I'm going to take away, I can take away this element. So B3 would be B1 union, the other way around. This is Y, and this is X. So it will be B1 union E and minus B. So it would end up looking CFE. Okay, that's not a great drawing, but as you've seen already, possibly understood, they're not the best at drawing. So that is how we can sort of exchange. So it's usually called a basis exchange axiom, that you can exchange an element for the other and still get a basis. You just have to be careful what you're choosing. Cool. Now we'll look at another interesting set in the graph, which they're called the minimal dependent sets. So we have independent sets, that's, they just have to be forests or trees. And then we have the maximal independent sets. So anything everything smaller than them is independent, and nothing bigger than them will be, or anything that contains them will not be independent. Now we're going to look at minimal dependent sets. So minimal dependent set, minimal here implies that any proper subset of the set will be independent. Okay, so this is minimal dependence. Say we choose a set in here, any set, and if we take their subset, then that will be independent. And we already know what the independent sets are, right? So what are the sets here that we can find inside the graph? A set of edges such that any subset of them, any proper subset, sorry, not just subset, any proper subset of that will be a forest, but the set itself will not be, will contain something. Cool. So if we take B, C, D, E, I'm just going to mark those. So this is B, E, D, C. Now this is definitely not a forest, but if I take away any edge from here, if I take away C, for example, I have BED. If I take away D, I have CBE. And any edge I take away, I end up getting a spanning tree. That's perfect. So this is an element of what we're going to call curly C. So curly C is going to, it's going to have elements like B, E, D, C. Now, what are those? Oh, yes, I missed your answer there. Yes, I was just going to ask. Yeah, so these are just cycles in the graph, right? So any cycle you pick up in the graph, say BFE or FCD, they're all cycles in the graph, and hence we call this curly C. They give you any subset of them will be independent, right? Any subset of them is going to be a tree. A tree is only one, you add an edge to a tree and then you get a cycle, or it contains a cycle. So if they're minimal dependent, then it has to be one away from a cycle. Now, what about the subset of a cycle? Say if we know C1 is in curly C, so if we already know that C1 is a cycle and C2 is a subset of C1, what does that say about C2? If we have a subset of a cycle, what do they look like? True. What if I force it to be an element of C? So yes, a subset of a cycle may or may not be an element of I, but what if I force that element to also be in curly C? What if I force an element C2 to also be a cycle? What can we say about C2 and C1 then? So a forest cannot be a circuit, a cycle, right? Because they're the minimal dependent set. So a forest is not dependent, a forest is independent. So if C2 and C1 are both cycles, and C2 is a subset of C1, what can we conclude about C1 and C2? So imagine we walk around, a random graph, we get a cycle. And say we have another cycle that's a subset of it. Say I start at a vertex, sort of walk, I walk. And I have to keep walking till I reach there. I can't sort of take a detour and come back, right? Because I know it's a subset of that. So then I end up getting the same thing. So if they're both subsets, then I know that C1 is equal to C2. There's no other way that I can get that. Okay, so my the first axiom actually would be about the empty set. Will the empty set be in curly C? Will it be a cycle or not? So my curly axiom 1 is about phi being in curly C. Will the empty set be in C, in curly C? We'll have to think about what happens in I1. So we know that in I1 we say that the empty set is independent. And here we're looking at the minimal dependent sets. So for sure, it's not going to be anywhere near a dependent set. So phi, yeah, it's a bit confusing, I agree. I had to get, it took me a while to wrap my head around all these axioms. So phi, because it's in the independent sets, it's non-dependent, therefore it's also not minimal dependent. So phi is not in curly C. And the second one is that property that we just explained, that if we know C1 and C2 are both elements of curly C and C1 is a subset of C2, then they just have to be equal. They have to be the same cycles. If one of them is a subset of the other, there's no way that you can have a proper subset which is also a cycle. The final one actually makes a bit more sense with cycle structure and graphs. So say I have, sorry, I'm going to skip that one. Say we have a red cycle, which I'm going to call C1, and I have my yellow cycle, which I'm going to call C2, and I have some overlapping edges here, right? So there's an intersection between C1 and C2. C1 intersection C2 is not equal to phi. And what happens if I want to create a bigger cycle? How can I do that? I can sort of start at C1, keep walking along the edges, and then move here and walking along the edges and going through that, intersecting vertex. And now I get a bigger cycle, right? So I have this cycle, which I'm going to call C3, which is a subset of all the edges that are in C1 union C2, right? So this is a property that you can only observe with these cycles in your graph, which I'm going to write down as curly C3. It's the axiom that if you have C1 and C2 in curly C, such that there is an element in the intersection of them both, then you can always find a cycle which is contained in the union minus that intersecting element. So say we here have an element E here, we can always take that away and still we'll be able to find a cycle that is contained in the remaining set of edges of C1 union C2. Okay, so that is C3, and together they form the axiom of all circuits. So this curly C is called the set of circuits in the graph. And the cycles in a graph are exactly what form the circuits in the graph matroid. So because the matroid here is defined, or the circuits of this matroid is defined on the cycles, we call this the cycle matroid. So a cycle matroid is a matroid that arises from these cycles, or the matroid is defined on the edges of a graph, such that the circuits are the cycles of the graph. Okay, so we take the cycles, we know that they already have these three properties, and we know that that is a matroid structure that we look at. So I'll sort of stop with this last slide here. If we quickly go through what the cycles are. So I've just added an extra edge for a bit of a, spice. So if we want to find out C here, we know we can look at all, so just A by itself will be one cycle. So that will be in curly C. And then I'm just going to write down the edges without commas just to save a bit of time. So we can, have the triangle cycles. So we have BEF, CDF, and of course you can keep adding to them in the chat like you've done before. BCDE, you've got the big one, the 4 cycle, and of course wherever there is D, you can also substitute with G and you get the same kind of cycle. So if, for example, with CDF, you can also say CGF is a cycle, and so on. So this will be a nice exercise if you want to continue, find out all the cycles in this graph, and all of those cycles together, they form the circuit in a set of all circuits in this matroid. And like as I said before, this is why the structure is called the cycle matroid. I had a bit more planned, but I think this is a good place to stop. So what we've done so far is we've looked at the independence axioms, roughly what they mean in the context of graphs, how graphs, what sets are independent in graphs, and we've looked at bases, what the bases are in a graph, and we've also looked at cycles, which is sort of the easiest one. So, but it was I wanted to get you there to the end, so starting off with the independent sets, and I highly encourage you to look at, if this looks interesting to you, to look at what happens in the world of vector spaces and how you get a matroid when you look at a bit of vectors. DG, yes, DG will also form a cycle. Yep, that is true. So that will be the only two-element cycle in here. And I will skip through this material. So my references are Matroid Theory by James Oxley. So that's like this, it's a big textbook, but definitely go through the first chapter if you want to sort of get a bit more of a touch and feel for what Matroids are. And definitely for the formal definitions, and some examples. He's got great questions too. And one of the articles that I came across when I was looking at matroids during my postgrad days was Matroids You Have Known by David L. Neal and Nancy Anidoda. And it's a pretty good article. It's a short read, few pages only. And it's a great introduction to matroids if you want to learn more. And of course, I'm happy to answer any questions now or even later. Swetha ma'am can definitely give you my email. I'm happy to answer that or point you to whoever can answer that question. And I think I'd like to stop here. Very thankful again to all the organizers for giving me this opportunity. And it was such a pleasure having such an interactive audience. I know it's quite hard to interact, or even for people to speak up. Like I've been on the other side of this too, if you want to answer a question. So thank you for everyone who's kept the chat box busy. Yeah, I think I'll stop now.
Thank you, ma'am. Thank you for this valuable session. Now I invite Ms. Alinda S. Vidyathil, second PG Mathematics, Sacred Heart College, to deliver the vote of thanks.
Good evening all. On the behalf of Sacred Heart College Chalakudi, I am here to offer vote of thanks on this National Enrichment Program. First of all, I extend a very heartfelt thanks to our chief guest, Dr. Meenu Mariya ma'am, for joining with us and for giving a wonderful session on Introduction to Matroid Theory. It was very helpful and interesting. Thank you, ma'am, for spending your valuable insights on the topic. I am also utilizing this opportunity to express my gratitude to the organizers of the session. My deep sense of appreciation and thanks to participants. Once again, I thank you everyone for being with us in this evening. Thank you.
Thank you, Alinda.